Welcome. In our previous video on multi-table operations, we discussed the join. Specifically, we discussed the inner join. Recall that when we formulate an inner join, we're accessing two tables, and we express some kind of relationship or join condition that informs the system of how to take rows from one table and match them or pair them with rows from the other table. The result of the inner join will be only those rows that satisfy the join condition, only the matching rows. We're now going to investigate another form of join called the outer join. When we form an inner join, there could be rows from either one or both of the tables that fail to satisfy the join condition, thus they don't appear in the result. But when we apply an outer join, we have the ability to preserve the rows from either or both of the tables that had non-matching rows. So let's take a look at this in some detail. Let's begin with the question, what is an outer join? We answer this by referring back to an inner join. Recall that an inner join produces a result set or result table that contains what I've called matching rows from the two tables. The match is the result of a row from one table having the same value as a row from the other table in the columns that are used to express the join condition. In this example, the condition is equality. We're forming what's called an equijoin. So we're looking for staff members who have the same value in their department column as exists in some row in the department table's department column. So the inner join will reflect only these matching rows. However, there are times when we want to include in the result all rows from a table that don't satisfy the match. This is the idea behind the outer join. First, we should qualify this and say that most often when someone refers to the join operation and does not make it clear what type of join, they're very likely thinking of an inner join. And our first video addressed details of that type of a join. Recall also that in the video we indicated that an inner join could be expressed using comma-separated syntax or the condition join syntax. This example is showing the condition join syntax. Recall that we also indicated that it was just a difference in syntax. There was no difference in functionality. With respect to the outer join, the comma-separated syntax is not standard. It is proprietary to a particular database. The syntax employed by Oracle database is a bit different than that used by Microsoft SQL Server, although they both support a form of comma-separated outer join. To avoid confusion with proprietary syntax, in this discussion we'll emphasize the condition join syntax, which is standard. The outer join preserves the unmatched rows from one or both of the tables. There are three forms of the outer join. There's a left outer join, a right outer join, and a full outer join. The form that is used determines from which tables the unmatched rows will be preserved. In the case of left outer join and right outer join, the unmatched rows are preserved from only one of the tables. But in the case of full outer join, we preserve unmatching rows from both tables. Before we explain the details of how the outer join works, let's consider why we would want to use such an operation. That is, why would we include non-matching rows in the output of a join? Why would we access multiple tables, then show data that exists in only one table and has no matching data in the other table? These are good questions to consider, and as we answer these, we'll explain the purpose of the outer join. Consider the inner join between staff and department. Recall that staff and department are not formally related within a database. That is, there is no primary key, foreign key, or referential integrity type of relationship here. Staff represent a kind of employee who are assigned to some department, but there's not a constraint on the department to which they're assigned. The department to which they're assigned does not have to appear in the department table. When we form the inner join, as we've done here, what happens is we express a join condition, in this case equality, it's an equijoin, and what we get is rows with a value in the department column of the employee or staff table have the same value as the column found in the department table's department column. Thus, for Dick Nix, he's assigned to philosophy, and he matches the philosophy department. For Luke, he's assigned to theology, and he matches the theology department. But if you recall, for these two tables, we have additional departments, and we have additional employees. We have Euclid, Archimedes, and Da Vinci, whose department ID is not present in the department table. And we also have in the department table two departments, CIS and management, which currently don't have assigned to them any staff members. Because there's not a formal relationship here, we can have values in what we might have thought to be the foreign key, the department column in the staff table, that are not present in the primary key of the department table. So in this case, if we wanted to show those staff members who are currently not assigned to an existing department, that is a department defined in a department table, we somehow need to preserve those non-matching rows if we're performing a join between these two tables. And likewise, there may be the need to pick up those departments that currently have no employees assigned. So that's the rationale or motivation behind the outer join. So let's take a look at how we actually accomplish this. Let's begin with a look at the left outer join. Our goal in our example will be to produce a list of all departments. Some of these departments will have employees assigned. Other departments will not have any employees. We can obtain the list of departments with assigned employees by formulating an inner join. It turns out that an outer join actually starts with an inner join and then goes beyond that to include non-matching rows. The outer join will continue by preserving or including within the result those departments that currently do not have employees assigned. Now let's take a look at the result table. When you form an inner join, you'll have columns from the department table. You'll have department, D building, D room, and DCHF&O. And you'll also have columns from the staff table, E name, E title, E salary, and department. However, when we have non-matching rows, we won't be able to populate all of those columns. So in the case of a department that currently exists without any staff members assigned, what values should we put in E name, E title, E salary, and department, the columns coming from the staff table? Well, there will be none supplied from the staff table because there's no matching row. If we think about it from the perspective that for those departments that don't have staff members, those staff columns don't apply, then it would seem logical to place null values in there because E name is not applicable, E title is not applicable, and so on. That's exactly what the system does. The system will concatenate the rows using columns from both staff and department, and for the table that cannot supply a matching row, null values will automatically be placed in those columns. These are referred to as null extended rows. Here we present the code to accomplish the left outer join of department and staff. Let's discuss this in some detail. Note that join is a binary operation. It operates on exactly two tables. Furthermore, the join operation is an infixed operator. It is specified between the two tables involved in the join operation. This is similar to arithmetic operators, such as 2 plus 3, 4 times 7, with the arithmetic operator falling between the two numbers or operands that are involved in the operation. So this means that we place the name of one table to the left of the operator and the name of the other table to the right of the operator. So we're saying department join staff, but we're also saying this is an outer join. Furthermore, we noted that there are three types of outer join: left outer join, right outer join, full outer join. Here we're specifying left outer join. The significance of this is that the result will include all rows from the inner join of the two tables plus the extra or non-matching rows from the left table, the table that appears to the left of the outer join operator. In this case, that is the department table. So when we use a left outer join, we are saying that we want to preserve non-matching rows from the table whose name appears to the left of the join operator. The table whose name is placed to the right of the join operator will be treated the same way it is treated in an inner join. We will see rows from this table only if those rows find a match in the other table. Because all rows in a table must be structurally alike, that is, having the same number of columns, the rows from the left table will be null extended to accommodate the columns that are coming in from the staff table. Remember, here we're saying select asterisk. We're selecting all of the columns. This means that a null value will be placed in each position that would have been populated by a matching row from the staff table. In the query to illustrate the left outer join, we displayed all departments, regardless of whether the department currently employed any staff. What do we do if we wish to display all employees, regardless of whether their assigned department is in the department table? We need to make the employee table preserve all of its rows. Using the previous query for the left outer join, we simply indicate that it is the right table, the table listed after the join operator, whose non-matching rows will be preserved. A right outer join is achieved by specifying that the right table will have its non-matching rows preserved. We can keep the tables listed in the same order. We simply change the word left to the word right, and attention is given to the other table. So do we need both the left outer join and the right outer join? We saw that the left outer join specifies the first table, the table that appears to the left of the join operator. If we switch the order of the tables, then we can accomplish what we just showed as a right outer join by using a left outer join. Simply reposition staff so it appears to the left of the outer join operator and specify left outer join. So in that sense, we don't need both. Keep in mind, though, that in these examples, we are selecting asterisk all of the columns. Therefore, there would be a display difference. But if we choose to select only a subset of columns, then we really don't need both the left outer join and the right outer join. Another operation is the full outer join. In this outer join, we preserve unmatched rows from both of the tables. But it's also possible that there might not be any unmatched rows in either table. So we can state that the full outer join preserves unmatched rows from one or both tables. It's targeting the potential to preserve unmatched rows from both tables. Simply use the word full, and then if there are staff members who are not assigned to a department, those staff members will be preserved. If there are departments that do not have staff members, those departments will also be preserved. So to summarize, full outer join produces the same rows as the inner join plus all non-matching rows from the left table and all non-matching rows from the right table. We make the comment that in practice, the full outer join may have limited practical value. Think about that for a moment. Tables that are related through referential integrity will often not have non-matching rows. Of course, this depends on the delete rule of the foreign key. Let's take an example to illustrate this point. Here we're looking at course and department. Remember, there is a relationship defined to the database that exists between these two tables. A department is an administrative unit. A course represents some kind of potential offering at the school. A department is responsible for many courses. So a department sponsors many courses. A course must be sponsored by a department. The foreign key in the course table is C department. It makes a reference to the primary key of department in the department table. Because every course must be sponsored by some department, the foreign key cannot be null. The inner join of course and department will give every course, that is, every child has a parent. So if we conduct an inner join, we won't miss any courses. There are no non-matching courses. A department might not sponsor any courses, so it is possible that there could be a parent that currently has no children. And in our current state of the database, the management department currently does not sponsor any courses. So in that situation, the full outer join produces the same result as the right outer join, here because we've stated department as the right table. In our previous discussion on inner join, we mentioned two ways of formulating the join. We could use comma-separated syntax, or alternatively, we could use condition join syntax. In either case, we indicated that it was possible to include additional filter conditions above and beyond the join condition. We said in the context of condition join that the filter conditions could be applied either in the on clause or in the where clause. It made no difference in terms of the result. Let's quickly review the idea in terms of the syntax. Suppose we were joining two tables, call them table 1 and table 2. We expressed the join condition, and then we add the filter condition. That filter condition could be either in the where clause or in the on clause. Our discussion of outer join has evolved around the condition join syntax. We note that it is possible to include filter conditions in an outer join, and these also can be expressed either in the on clause or the where clause. What we want to discuss now is the fact that if you include the filter condition in the on clause, you may get a different result, a very different result than what you might get in terms of including the filter in the where clause. Furthermore, a filter can be applied to either the left table or the right table, and that has important implications as well, depending on the type of outer join that's used. So let's take a look at this left outer join and discuss this in some detail. And then we'll show some variations on this and some additional outer joins as we examine very closely the idea of including filter conditions in an outer join. The current query involves the course table and the class table. So let's examine these tables. If we run a query against the course table and simply select all of the rows, we'll find that there are 14 rows in the course table. Furthermore, recall that CNO is the primary key of this table. Hence, it's a unique identifier. If we examine the class table, selecting only those rows where the CDay column is equal to the value of Tuesday, we'll find we get exactly one row. So the class table will provide one row. There are 14 rows in the course table. If we perform an inner join, we will get one row in the result. Let's make a general statement regarding the left outer join, which is what we want to examine here. When evaluating a left outer join, each row in the left table must be included in the result, regardless of whether there is a row in the right table that matches the criteria in the ON clause. Thus, with the inner join and the predicate of CDay equals Tuesday, we'll get one match, one row in the inner join. But the outer join should give us all 14 courses. So let's make some further observations about this particular query. The query is a left outer join. The left table is course, the right table is class. The filter that is applied is specified within the ON clause and is applied to the right table. When this outer join query is run, the result of the outer join contains 14 rows. Thus, we should expect at least 14 rows in the result because the cardinality of the left table is 14. However, inclusion of rows produced by an outer join does not mean that all rows will appear in the query result table. Rows produced by the outer join could be excluded from the result by filter predicates. The filter predicate that we're applying here is applied in the ON clause. This predicate will be applied before the outer join is evaluated. This means that the right table will have only one row, hence we will get 14 rows in the result of the query. In our next version of this query, we'll move this filter predicate to the where clause. This will have a different result on the output. When we modify our query by placing the filter condition in the where clause, the query result is quite different. The result of executing this version of the left outer join produces a single row. The filter is applied after the outer join has been performed. To better understand what's happening, let's consider the outer join without any filters. If we run the outer join without a filter condition, the result table consists of 16 rows. There are 9 rows in the class table. Each of these rows will find a matching row in the course table. Thus, these 9 rows form the inner join portion of the result table. There are 7 different CNO values found in the class table. This means that 7 of the 14 rows in the course table will not find a match in the class table. This is where we get the additional rows of the outer join. Thus 9 plus 7 equals 16, which is the cardinality of the result table for our outer join with no filters applied. If we then proceed to apply the filter, which is what happens when we include the filter in a where clause, then there will be only one row among those 16 that satisfies the condition of C-day being equal to Tuesday. Hence, the result of the query produces exactly one row. Continuing our examination of the left outer join, we'll now consider what happens when you apply a filter to the left table. Such a filter can again be applied before or after the outer join processing occurs. When the filter is specified in the where clause, it will be evaluated after the outer join has occurred. That's what we're illustrating with this particular query. So this query will produce 7 rows. That's because the course table has 6 rows for CIS-sponsored courses. In the class table, we have scheduled offerings for courses C11, C33, and C55. In fact, there are 2 sections of C11. There are no scheduled offerings of C22, C44, and C66. So the rows in the query result will show C22, C44, and C66 as null extended rows, while the other rows in the result of the outer join will show the class information together with the course information. Now, although the outer join itself will include courses for theology and philosophy, no such courses will appear in the result of this query because of the time at which the filter is applied. The filter is included in the where clause, so the filtering occurs after the outer join has occurred. Thus, it removes the philosophy and theology courses. In order to be thorough in discussing the left outer join with filter conditions, we should answer the question of what would be included in the query result had we placed the filter in the on clause. Previously, we had indicated that when the filter is included in the on clause, that filter will be evaluated before the outer join processing occurs. Well, the same will be true here. What will we get? We'll get a total of 15 rows. 7 rows will result from the CIS department. Remember, we have 6 distinct CNO values, but one of those values appears in 2 rows in the classes. We have 2 scheduled offerings. Therefore, 7 rows will result from the CIS department. Additionally, theology is responsible for 4 distinct course numbers, and philosophy also is responsible for 4 distinct courses. So 7 plus 4 plus 4, we end up with 15 rows. So in terms of the sequence of events, or the timing, we could consider what happened here as first, get the CIS courses, apply the filter, then perform the outer join. Although the outer join operation seems relatively straightforward, we now realize that using the ANSI SQL Standard with the condition join syntax, that some thought has to be given to when the filters should be applied prior to writing your outer join query. So this wraps up our discussion of the join operation. So what have we covered in these 2 videos? We indicated that a join operation is a multi-table operation, which brings together data or rows from 2 tables. We had indicated that it's kind of like a concatenation of the rows from the 2 tables, appending the columns from one row to the columns of the other row. Again, we noted that join, strictly speaking, is a binary operation. There is no such thing as a 3-table join or a 4-table join. But when we perform joins, we can do a join of 2 tables, which produces a new table, which then can be joined to another table. We talked about the inner join as returning rows that satisfy a join condition. Our primary examples used equality for the join condition, so we talked about equijoins. But we're not limited to equality. We talked about the concept of a theta join. Basically what that means is we can use any operation. It could be less than, greater than equal, and so on. The result of an outer join includes what is produced by the inner join plus additional rows from one or both of the tables. Recall that we talked about three different varieties of outer join: a left outer join, a right outer join, and a full outer join. We had indicated that we really don't need both the left outer join and the right outer join because the operations are all relative to the placement of the tables, whether the table appears to the left of the join operator or the right of the join operator. The full outer join also has limited practical application due to the idea of referential integrity and delete rules. Very often the delete rule is going to be such that you would say on delete restrict or on delete cascade, in which case what you have is all foreign keys from the child will match a row in the parent table. Thus, you're not going to have extra children. You'll have only extra rows from the parent. We also indicate that by looking at the ANSI standard condition join syntax using the join keyword, that conditions can be expressed either in the on clause or the where clause. What I suggested with the inner join was to express the join condition in the on clause and put filter conditions or filter predicates in the where clause. When we discussed the outer join, we saw that the filter condition could be applied in either the on clause or the where clause, but it changes the question being asked. It changes the semantics. So hopefully you found this to be informative, and obviously the outer join has some complex subtleties that we must be aware of.